Alright, welcome to my high school chemistry lecture series. I will be having lectures and then also chemistry demonstrations that demonstrate certain points from the lecture. So, to understand chemistry, I would say the basic first thing you should learn about is the atom. Because the atom is the fundamental building block of all of chemistry. So, you might be scared now. Oh no, we're going to talk about atoms now. These are scary. But really, if you go back to the ancient Greek times, when people first started thinking about the concept of an atom, it's quite interesting and doesn't require any scary mathematics. It's more philosophical, if anything. So the Greek word, and this is of course the transliteration, atmos. Atmos. Actually, I should write that bigger, but atmos means uncuttable. And this concept of getting to a point where there is some kind of particle or some unit that cannot be split anymore, most people would attribute it to the ancient Greeks. And I'm going to try to get to this atom or atmos level with a plumb and a kitchen knife. So if I start by cutting the plumb in half and then taking the piece away and just cutting the remaining piece in half, you'll see that there is absolutely no way that I could ever hope to get to any level where I can't split, where I fundamentally can't split the plumb anymore. Obviously this piece is so tiny I'm just squishing it with the knife, but that's the limitation of this kitchen knife. It's not a fundamental new or fundamental particle of plumb. Well, with tools much fancier than kitchen knives, people have actually been able to indirectly see down to the atomic level. And it turns out that there are many different kinds of atoms. And it turns out the Greeks were partially right. There is a kind of fundamental particle, although nowadays we can actually split them further. But I'll talk about that later. So these different kinds of atoms, if you have enough of them that you can actually see them with the naked eye, then they make up these different substances, and we call these substances elements. Now, some of these elements I'm sure you've heard of, and I'll give you some examples of those. One of them is copper. Copper is an element. There is a copper coin. Another one is silver. There is a silver coin. And another one is gold. There is a gold coin. So these are elements, and they are made up of many, 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 many atoms, and I'll talk about how many in a little bit. Now, some people get confused between an element and an atom. Let me make this very clear. An element does not equal an atom. It is not the same as an atom. An atom is the fundamental smallest unit of an element, and the element is the substance itself, like the gold, silver, or copper that you see here. So that's a difference. You should keep that in mind because many people get confused with that. Now, it turns out that actually you can split atoms, but the thing is, if you split atoms smaller, they'll lose the element's properties. Let's say I took this gold and I got down to its one gold atom, and then I split it further. It would no longer be gold. That's why I say the Greeks were actually partially right. Let me give you a more macroscopic demonstration that maybe you can relate with more. Here is some fruit salad. Now, if we pretend that fruit salad is some kind of a specific substance, we'll call it fruit salad. Well, now let's try to get down to the smallest unit here that is still fruit salad as opposed to a specific fruit. So if we take out a pineapple, and we take out a plum, and let's also take out a banana. Well, there aren't any other fruits here. So if we bring them all together here, and they are exactly in the same ratios here. So if we bring this together, this could be considered an atom of fruit salad. Now, it's not actually an atom because atoms only refer to the smallest unit of elements, but it is the fundamental unit of this fruit salad over here. If I were to try to separate this further, say take away the pineapple from the banana and the plum, well, I did split it, but this isn't fruit salad and neither is this. This is pineapple and this is banana and plum. If I split it again, well, this is pineapple, this is plum, and this is banana. So while I was able to split it, it's no longer fruit salad. That's what I mean, that you can split atoms, but they will lose their properties if you split them further. All right. Now let's get into the structure of an atom. So I did say that, you know, people have been able to split these atoms, and I'll show you what the actual particles that make up an atom are. So an atom you can think of it as having a center, or a nucleus, it is sometimes called. So I'm going to model for you right now the hydrogen atom. And the hydrogen atom, so this is, let's see, all right, this is hydrogen, and H is the symbol for hydrogen. So a hydrogen atom has a nucleus consisting of one particle, which I'm going to represent as a little red dot, and that particle is called a proton. So in a normal hydrogen atom, there is one proton in the nucleus, and there is one electron flying around it. So this little orange dot is an electron. So these two, protons and electrons, are two of the fundamental particles that make up atoms. But there's a third one, and for that I'm going to show you helium. Helium, which is, the symbol is He, has, here I'll just designate this as the boundary of the atom, although if we talk quantum mechanics, we'll see that there isn't really a definite boundary of the atom. But helium actually has a proton, another proton, and it has two of these other particles called neutrons. And I'm just designating these as blue. They obviously don't actually have, they're not colored in this way, but I'm just designating it. And it has two electrons orbiting, well, not exactly orbiting, I will talk about that later, around the nucleus. So I'm going to label this new one a neutron. So that is a neutron. Those are neutrons. Alright, so you may be asking yourself, the hydrogen atom has one proton and one electron. The helium atom has two protons, two neutrons, and two electrons. Which elementary building block here of the atom determines what the element is, or what kind of atom it is? And it turns out that the answer is quite simple and straightforward. So it turns out that the number of protons in the nucleus determines the element. And the number of neutrons in the nucleus determines the isotope. Alright, so here I have it all written out. The number of protons in the nucleus determines the element, like, for example, silver or gold. The number of neutrons in the nucleus determines the isotope, and the isotope, they're all the same element, and they have very similar, basically the same chemical properties, but they just have different weights, different masses actually. And the number of electrons determines the oxidation state. Now that probably sounds like isotope and oxidation state. Oh my god, two new terms. One of them has 2 words in it. This is probably scary. This is pretty scary. But all an oxidation, what an oxidation state is actually, in some ways, it refers to the charge of the atom. Which brings me to another point. Protons are positive. Alright, so another thing I want to make clear is actually, so protons are positive, neutrons are neutral, and electrons are negative. And this, we're talking about electric charge. Here. And that leads me to another point, one of my final points, which is, well, why do the electrons actually stay in the atom if they're flying around the nucleus? Well, the answer has to do with this. If I, let's say, have a carbon atom, and the normal isotope of carbon has 6 protons and 6 neutrons, so I'll do 6 of each. This is absolutely not drawn to scale. 1 more of each. Alright, let's say that's the nucleus of a carbon atom, and I'd have 6 electrons, and I'm drawing them as orbiting, but really don't think of it as orbiting. Think of it as kind of the electrons are not in the nucleus, and there's a probability of finding them anywhere, actually anywhere in the universe, but there is a specific point where the probability is highest, and it drops off very quickly off from there. The probability of finding it, say, you know, in the Andromeda galaxy is you know, obscenely low. But, you know, they're in this kind of probability cloud, and the reason that they don't just fly off is that they do have energy, so they stay out from the nucleus, but they are negative, and the protons in the nucleus are positive, and as you probably already know, opposite charges attract. So the electrons are also drawn towards the nucleus. Alright, and that leads me to another point, which is about notation. So this is just a quickie. How do I indicate what isotope, oxidation state, and element I'm talking about? So the simplest way is just to write the symbol of the element, which you can easily find on the periodic table. And so let's say I'm talking about carbon. And then what I do is I'd write the number, and we know carbon has 6 protons. That's carbon by definition. So then, if I write the number of protons plus neutrons, I'll do that in a new color, so, alright, protons plus neutrons, then by a little bit of arithmetic, you can figure out, well, what isotope am I talking about? How many neutrons does it have? And then if I want to also indicate how many electrons it has, if I write nothing, that is neutral, meaning that it has the same number of electrons as protons, or 6. But if I, let's say, write plus, that means it's missing 1 electron, has a +1 charge, because protons have the equal positive charge as electrons' negative charge. So that would mean it has 5 electrons. If I write 2 plus, that's 4 electrons. If I would write minus, that means it's got 7 electrons, etc. Additionally, there's an optional part here. If I can also just write the number of protons right here. I could write 6, but that's optional. We're now going to take something that might seem like an element and see if it actually is one.